Hi, everybody. Welcome. We're going to talk now about inductance applications. So, what is inductance? Inductance is the basic role of inductors to prevent any sudden changes in current from flowing through it. So, inductors act as resistors when current is increasing, and when current is decreasing, the inductor behaves as a makeup power source, which is kind of cool. It's an interesting thing. So we talked about capacitors. Inductors are really the current storage device. It can store current and provide resistance as it's kind of packing away that current, and then it can provide makeup current power when the current is falling down. Let's just look at how an inductor does this. So when current is varied through a conductor, it carries a secondary EMF. So it's producing an electromagnetic field. That's what EMF stands for. In normal wires, it's negligible. It doesn't do much because we've just got a straight wire and it's just a tiny field that surrounds that one wire. But when we coil those wires up, they have the effect of concentrating that magnetic field and allowing a larger magnetic field to be generated. Essentially, each of those wires kind of acts like a roller conveyor in essentially adding additional oomph to the EMF field that is being generated. As the current is increased, the EMF operates opposite that direction of current. So that electromotive force, the EMF, the electromotive force, is going opposite the direction current's currently going, and that has the tendency to make it seem like resistance. Okay, and we'll get into the difference between inductance and reactance, reluctance, and and impedance later. But that's a subject for a different video. But what's important to understand here is that as current is increasing, we're pushing back against that current with the EMF, so that acts as a resistor. So the greater the rate of increase of our current, the greater the reverse or back electromotive force. And that lasts only during the change. And then once that happens, like once our current is steady, current passes normally. So that's the resistance part. The power source part comes in when current decreases, then the EMF flows in the same direction as current. So this will momentarily maintain the current as the magnetic field collapses. So like it's almost like we're storing energy in a magnetic piggy bank. Or it's like when we're inflating a balloon and then we let the balloon, like we take the pressure off of the balloon and then it blows out until it's stored. So if you think about it like we're inflating a magnetic field and then deflating a magnetic field, and that energy goes, like that energy is a resistance as we're inflating that. You know that because anytime you inflate a balloon, you're met with resistance when you're doing it. And then that resistance then turns into power later on, et cetera, et cetera. There's multiple other ways of looking at it. And one of the more effective ways of looking at it is like using the water analogy, which we can use the same way we use it for like voltage. Voltage is pressure, and current is flow. Well, in a hydraulic system, we can think of it, an inductor, as an inline turbine attached to a flywheel. A flywheel is just a heavy mass. If you've worked with lawnmowers or old-timey engines that had flywheels to it, it's a mass that's just maintaining inertia to keep something spinning. So if we have an inline turbine or even like a water wheel, essentially that flywheel is just maintaining it if all of a sudden our flow from the water stops. So as the water flow increases, the turbine itself and spinning up that heavy mass of the flywheel creates a resistance to that flow. So it creates a resistance to the flow of water through that turbine until it has spun up to match its speed. And then once it matches its speed, once it matches that flow, it's going to continue to go at that and it'll proceed as normal. However, if the flow decreases, the turbine will continue to push water through it because of the mass of that flywheel. It's essentially creating a momentum to it. It's inertia that will continue to pump and push water through until that wheel slows down. So that's the water analogy for this. It's a way of visualizing it. It can be very helpful to kind of know that water analogy. Inductance, or L, is expressed in henries, which makes total sense because Henry starts with L, I guess. No, L, for whatever reason, and henries, I guess because Henry thought of it. 1 Henry equals 1 volt per 1 amp per second. So unlike a lot of our other definitions, this one contains time in it. So inductors in series add their so it's important to realize that this is a sort of how fast, like this is when we were talking about how fast we change the current, is how many volts we're going to get. That's why there's that per second there. Inductors in series add their inductance just like resistors, and inductors in parallels have an inverse addition exactly like resistors. So we deal with inductors the same way as resistors, whereas capacitors are the exact opposite. Essentially what they are, if you were to boil it down to 2 words, is current inertia. Whatever current is happening, it's providing inertia to that current. It says, so they're really just coils of wire, right? So we talk about magnetic core, air core, what kind of core it is. A magnetic core, if we use a ferromagnetic rod inside of it, it could be an air core. It could be an adjustable one or a ferrite bead. But the long and short of it, most of these you're going to be working with primarily a magnetic core or an air core. Adjustable inductors are basically going to have contacts that basically allow you to skip to different numbers of windings. And like with this, we're really going to want to talk about some applications. So one of the main applications that you're going to see in our builds this quarter is relays. There are relays that are inside of your PLC. You'll hear them click when things go on. And a relay is basically an electrically actuated switch. Relays are used when it is necessary to control a circuit by a separate low-powered signal, or where several circuits need to be controlled by one circuit. You can use stacking up LEDs, or you can stack up relays in order to create logical programs even. The first relays were used in long-distance telegraph circuits as amplifiers because you could switch really high voltage, kilovoltage ratings for transmission across the country. Things that are 2,000 to 20,000 volts. You can do that safely with a relay, but if you think about a telegraph, you're sitting there going and tapping with a little contact there. Do you really want to be that close to 20,000 volts? No. So we use a relay, which basically uses a lower voltage to energize a coil that pushes the contact that closes the circuit on the much higher voltage, et cetera, et cetera. But yeah, it's similar. We use them all over the place for motor controls. When they're big, uh, they're called contactors. So there's three basic kinds. You have mechanical, you've got reed, and you've got solid state. So for high-powered applications, these are generally mechanical ones, and they're generally called a contactor. So you send, and we'll work with these later on this quarter. You'll send a signal to the coil. That coil will become a magnet. That magnet will force an iron rod to make contact with another circuit and close a switch. So that's what a contactor is. It's essentially a high power relay. Solid state relays are different than this. Solid state relays are not inductors. They are using semiconductors instead to perform that switching, so they kind of don't fall within this. And reed relays are for relatively small amounts of energy, and they essentially use the magnetism just between fairly easily flexible contacts in and of themselves to close or not close. There are overload relays that are essentially ones that have thermal faults, so they essentially break the circuit once it reaches a certain current level. They're called protective relays, which is another kind of relay that you'll see out there in circuit protection, and we will be dealing with those this quarter as well. At its heart, when we look at the symbols for these things, it's kind of the old question: is it normally open? Is it normally closed? Is it single pole versus double throw? Et cetera, et cetera. And so relays come in many of the same sort of switch architecture. The symbology of the switches is the same. The difference is that it's shown as controlled with an inductor. So this is the symbol for an inductor right here, and this is the symbol for a switch. And this line shows a separation between the two of these. These are on different circuits. So we would power this coil with a different circuit than what we're doing on this one. So it provides us that isolation to be safe when dealing with higher voltages, or to control things with a very low voltage that we can that we need to control something with a higher voltage. So this is just a wordy one. I'm not going to actually read through this for you, but it's here on the slide for you to look at. It just kind of very, very briefly describes all of the images on the previous slide. So we need to remember that the coils on relays are inductors, and as such they can cause very large EMF when current changes. There are transient suppressors that are generally used when we're dealing with large coils to make sure that EMF doesn't fry other things in our circuit. In DC, this is usually a diode in parallel, and in AC, it's generally a resistor and a capacitor in parallel. Quite often when we're dealing with these are actually built into the module itself. We're really talking about large coils, so things that are being used for large solenoids, large contactors, things like that. They generally put the transient suppressor in those modules. So it's kind of unseen, but it's important to know that it does exist in there, and that's something that is taking care of and taking the EMF worries off of our mind on those things. But if we're just dealing with a straight up coil, if all you're looking at is a straight up coil and that coil is large, you need to be aware that can create some problems when we try to vary the current through it. Inductors have a lot more applications in AC circuits, and so when we get to resistance, reactance, and impedance, We will actually kind of dive into detail on what inductors are used in AC. Um, but inductors obviously are all over the place. We can use them to transform AC into DC. That's something that we'll talk about in a later video. And so that and then there is also other items that you will see. Obviously, an inductance motor is a three-phase motor or a single-phase motor that uses coils in it. In fact, most motors use coils in them. They all have inductors in them as a part of it because they're generating a magnetic field to translate electrical energy into mechanical energy. So you'll find inductors all over the place. Now, the real reason why we're having this discussion here is so that you are aware of what also is happening when we have inductance. It's like, cool, great, we've got a magnet. And we can use a magnet for a lot of different things. We can use it in a solenoid valve, to change the position of that valve and allow hydraulic power or pneumatic power to go through that valve in a different direction. But that's also having additional effects on the circuit that we hook it up to, right? It is, in essence, just a wire. And if we're not careful about how we protect that from overcurrent and how we deal with current variance, is going to be key in whether or not we're successful in using that, because inductance works in both ways. It induces on itself as well. And so we have to be aware that it's really just kind of an inertia in our system. It will cause a resistance when it's powering up, and it will create a backup power supply when we turn it off, which means that when we turn it off, it's not necessarily just going to stop. So those are some things to keep in mind. Of course, we'll get more into relays are really the only use for them in purely DC circuits. So when we get into the resistance, reactance, and inductance talk later on, it will become a lot more apparent what those uses are in AC, and we'll be doing a lot about that. It also causes a phase angle shift, the same as capacitors. So we'll get to that when we start talking about things like Eli the Iceman. Things coming up. Not going to give the spoilers now. That's all I've got for you on this. So that's inductance for this week, and we'll see you in the next video.